Consider that if you take, for this setup that we are doing, if you use the conditions, what are the conditions? Let us write down the conditions. The conditions that we are talking about, the laboratory conditions under which this experiment is carried out. If you consider that, okay, if you consider that, D, what was D? The D was, if you remember, it is a distance between, look at this apparatus, this was D. The distance between this mirror and the first mirror is D. Similarly, upwards also it is D. So, if the distance D is considered to be something like, this is an experiment that was carried out in the laboratory. So, when they conducted these experiments, they have used these parameters that D is equal to, let us say 11 meters, okay, and wavelength, monochromatic light is what they have used. That means it is a sodium light which has, monochromatic means what? It has single line. So, the frequency and the wavelength that is used is 5.5 into 10 to the power minus 5 centimeter, and V is the velocity of ether. So, if V is the velocity of the ether, velocity of the ether is found to be 3 into 10 to the power 6 centimeter per second. This is what you are using. Then what else they have used? You all know the velocity of light is 3 into 10 to the power 8 meters per second, which is 10 power 10 centimeter per second. So, when we use these relations here and they calculated, when they calculated that, what did they observe? The fringe shift, one thing you have to keep this in mind is now, with these values that we are using, it's big enough now. So, with these values that we are using, initially if you remember, you have a mirror here, you have another mirror here, and this is one mirror. The light is reflected, going back, and it takes this path. I am just redrawing, you need not do, you have already done this. And then you have a mirror here, this is going like this, and these two, you have this telescope. Okay, now if the entire apparatus is shifted through 90 degrees, we saw shift of fringes. So, with this experimental setup that they have done, you have already seen this figure, I don't need to draw again. So, with these experimental setup, theoretically, substituting all these values into that figure, we get a fringe shift of 0.4. That means fringes should drift by 0.4 mm, actually shift. So, but when they carried out, this is theoretical. So, in physics what we do is we conduct an experiment, we calculate. We use theoretically, make use of the formula and calculate. We use theoretically, the formula is used and we calculate. And what else we do? We generally, what we do is we compare the results, what we get from these two. Compare the theoretical results with the experiment. Experiment and theory results are compared. When they compared, they could not get, this is very important, they could not get fringe shift more than 0.01. This This is a very alarming situation. They never got any result which is more than 0.01. But what is expected is 0.4. So that means there is some disturbance there. There is something, a flaw or a mistake. Something has gone wrong somewhere. Either theoretically it is wrong or experimentally it is wrong. Theoretically it cannot be wrong because they have just calculated by using these parameters. So theory cannot be wrong. That means there is something wrong only with the experiment. That means experimental thing only is not correct. Let us not say it is wrong. We say it is not correct. So this experiment has been carried out at different instances of time by different people at different times. Scientists will not be happy with doing the experiment once. They will be doing it many number of times, and after several conclusions, several experiments, what did they say? They said that the experiment could not locate this fringe shift, whatever we are saying. So that means to say that there was no either being present. This is a conclusion. This is a very important conclusion. I will write them again. Let us see what all they concluded. So the first thing is that ether was not present and all objects are dragged by ether was the assumption. Even this assumption was proved to be wrong. Even this observation is proved to be wrong. That means that there is no either shift. That is not possible. Either shift is not there. So then what do you conclude from this? That means that they prove that it is a null result. When you say null, what does it mean? It is not giving you any results which are positive. It is a null result. So there is no ether drop, there is no ether velocity. This is when our famous scientist, who is the famous scientist? Einstein, Albert Einstein, has proposed, because this experiment was proved wrong. Which experiment it is? Michelson's Morley experiment was proved wrong. Then Einstein proposed what is known as special theory of relativity. Special theory of relativity was proposed. And what is very important of this theory is, please make a note, all the objects in the universe, all the objects in the universe move in relative motion. That means nothing is absolute. Nothing is absolute. So what all physical, measurable quantities. What are the fundamental measurable quantities? Length, mass and time, which you studied in your intermediate. These are all relative in nature. All these length, when you say length is 5 meters, it is 5 meters short compared to 30 meters, or it is longer compared to 1 meter. These are all the famous, very familiar day-to-day examples that you can think of when you are talking about relative motion. Similarly, when you are talking about a person moving to the north, it is exactly opposite to the person who is moving in the south. That is with respect to the direction. And when we say we are in the southern hemisphere, that means somebody is in the northern hemisphere. So you say that the earth is moving from the west to east, and if you are viewing it from a different planet, you will be observing it in a different direction. So all these are relative. When you say you are moving very fast, you must be moving very fast at the rate of 60 kilometers per hour compared to a person who is moving only at, let us say, 10 kilometers per hour. But you are slower compared to a person moving at 100 kilometers per hour. Isn't it? Therefore, everything in the universe that we are talking about is all relative. Nothing is absolute. You cannot have any absolute measurement. Therefore, now let us consider what is known as the different postulates of special theory. The different postulates of special theory. Let us consider them. There are two postulates put forward by the theory known as special theory of relativity. The first postulate says what is it? That it's actually called principle of relativity. The first postulate is called principle of relativity. What does it say? That the laws of physics are the same. That is important. Laws of physics are the same in all reference frames. The laws of physics are same in all frames of reference. When you say this, laws of physics are the same, that means what are we referring to? We are referring to what is known as inertial frames. So in other words, we can say, what do we say? We can say that these frames in which laws of physics are the same are called inertial frames of reference. So that means the laws of physics are same in all. You can alternately, you can state it as, alternative way of stating this is the laws of physics are same in all inertial frames of reference. This is a law, this is a postulate, and it has to be written in the same way as is given in all your textbooks. Please don't try to change its definition. When you say its definition, it has to be stated in the same way. Then only you will get marks. Don't try writing definitions in your own words. Definition has to be written in the scientific, technical way as is being given. The second one, therefore, is, this is called the principle of, the first one was called the principle of relativity. The second one is called the principle of constancy of, the principle of constancy of speed of light. That means what we are talking about is the speed of light. This is a principle. So how do you state this as? The speed of light is same in all inertial frames of reference in all inertial frames of reference it is the same in all inertial frames of reference. Not only same, that is important, it is not only same but also is constant. Not only same and also, and it is also constant. Constant in all constant in all frames of reference. And what is the constant value with which the light is moving? The velocity of light is constant, and that it is equal to 3 into 10 to the power 8 meters per second, or 3 into 10 to the power 10 centimeter per second. And no other object in the universe, no other object in the universe can travel faster than that of light. No other object can travel faster than that of the universe, that of the light, I'm sorry. So what do you conclude from this is, what is the conclusion? Let me put them all in a big diagram here like this. So the first principle is called principle of relativity. What does it imply? It implies that there is no fixed frame of reference. There is no fixed frame of reference. And different observers observe the events. Different observers observe the events differently. We have already seen this case, isn't it? So this is the first point. This is the second point. The third conclusion is there is no absolute frame of reference. That means motion is considered to be always, the objects are said to be in relative motion. All the objects are expected to be in a relative motion. Now let us see, what does your second law imply? The second law implies, this is derived, the second law is derived from the Michelson-Morley experiment. What is it that we derived from this? Even though we say you have a light source. You remember you had a light source and light is coming and is falling on this mirror and it is getting reflected and it is getting transmitted, right? But the velocity we said, and we also said either was moving like this because of the earth, and the light source we said is moving with the velocity v. This is not correct. Though light is coming from the source, light is coming from the source. Source is this, but it is not moving with this velocity. Instead, it is moving with, what is it? Light is coming from the source. So we conclude that light is coming from the source. No doubt, light is coming from the source. But it is traveling with, the light is traveling with a velocity given by c. This is what it means. Light is coming, but it is coming and traveling with the velocity of light. So far so good. These are the postulates of your special theory of relativity. So that means to say your Galilean transformations, what we considered, also are not completely valid here. There is no constancy. So therefore, what is it that we are talking is, there is some other transformations and we call them as Lorentz transformations. Let us see what they are. These transformations are described this way. What is it? Let us see. Event is described, as we have seen, a particular event is described by different people in different frames of reference. This is what we have seen. So let us now once again consider two frames of reference. Draw two frames of reference as I have been drawing you. Let me take another color, let us say red. One second, girls. Draw two frames of reference in the meantime. I should draw this little different from what you have. So let me draw it like this. This is my x-axis and this is my y-axis. Okay, and this is my z-axis. So you have once again two frames of reference as before. Let's call this as S and let's call this as S prime. Okay, and S prime is moving, let us say, as before with the velocity v. This is my origin O. This is O dashed. So this is my x dash. This is my x. This is my y dashed. This is y. This is z and this is z dash. What is important is, initially, very important conclusion here is that we are showing that this velocity with which this frame is moving is v. So when do you say these are Lorentz transformations? When the velocity with which the frame S prime is moving, that is V, is equal to the velocity of light. When it is equal to the velocity of light, then these transformations are referred to as, Lorentz is a scientist, so the transformations are named after him and we call them as Lorentz transformation equations. These are therefore referred to as Lorentz transformation equations. Okay. So now let us see what they are. Let's talk about these transformations. So as shown in this figure, frame S is stationary and S prime is moving with the velocity V, which is equal to the velocity of light. This is what we assumed. Okay. So when we assume like this, let an event defined by x, y, z coordinates. So in S frame, the event is described by x, y, z and t. And in S prime frame, the event is described by prime coordinates and t prime. So at time t is equal to 0, as before, at time t is equal to 0, both the frames are originating at 0, 0, 0. Initially, to start with, both the frames are starting from the origin. Okay. When both the frames are starting from the origin, after t seconds are elapsed, after t seconds, the distance travelled is equal to, can I write x is equal to ct, because light is moving with a velocity c. So distance is given by distance by time is velocity. So distance moved is x is equal to ct. Let's call this as equation number 1. Now during this time, velocity of light being same, this is the frame, the event is moving by a distance x is equal to ct. You know that c is constant in all frames of reference, isn't it? So when c is constant, after t seconds, with respect to, this is with respect to S frame. So now let us consider with respect to S prime frame, the distance moved was given by, the distance moved in t seconds is given by x dash is equal to, c is the same, t dash. This is very important. C is constant. But measurement of time is different, measurement of distance is different, measurement of length is different, but velocity remains the same. So that means to say that distances measured in S and S prime frame are to be related. There should be a relation. They need not be same, but there should be some relation between these two. That means there is some proportionality that exists between, there is something called as a proportionality that exists between these frames of reference. Frames means it's understood, it's frames of reference. Okay, what is that proportionality constant that we are talking about? Let us assume that x dash is equal to, you remember x dash was equal to x minus vt using Galilean transformations. We made this as equal. Instead of making this equal, let us write some constant k, and we call this k as some constant. K is a constant. Since velocity is same, you can write like this. So if you write x dash is equal to x, may I write x is equal to k x plus vt prime. How am I writing? Because of relative motion. So if it is according to x prime frame, this is moving to the right, but according to x frame, it is moving to the left. So minus v plus v. So if this is the frame, if it is moving in this direction with v, it is moving in this direction with minus v. So depends on in which frame of reference that you are looking at and making measurements. So based on this, you will have different measurements. So you have relations 3 and 4 where the constant can be either k or k prime. Both are the same. So whether you represent it with k or k prime, it means the same. And our now job next will be to determine this value of the constant. So with this, let us now make an assumption. This assumption is again relative. Whatever assumption I am making may not be the same according to you, but let us have some consensus and say that with respect to some assumption that we make, with respect to S prime frame, with respect to this, S is moving with minus v velocity. Similarly, when I say S is moving with minus v velocity, that means according to S prime is moving with plus v velocity, isn't it? So when you have a relation like this, I am adopting it from Lorentz equations. And you already know what is x prime and what is x from equations 1 and 2. So let us substitute equations 1 and 2, equations 1 and 2 simultaneously in 3 and 4. That means in place of x, what should I write? I should write x prime. If I take x prime, equation 3, let me take only first equation 3. Equation 3 was x dash is equal to k into x minus vt. So in the place of x dash, what will I write? I write it as ct dash is equal to k. Again x, what will I write? ct minus vt. So what is common? kt into c minus v. So this becomes my equation 5. Similarly, the other equation ct, that is x, is equal to k. X prime was ct prime plus vt prime. So this can be written as equal to k t prime c plus v. So far so good. Now you have developed two more equations. Multiply multiplying 5 and 6. I am doing mathematical part. Just copy down the mathematical equations. Let us see the significance of these mathematical equations in a few steps more now. So when you do this, when you multiply these two, what do you get? Ct dashed. This is Ct dashed, isn't it? And Ct dashed. So what do I get? I will get here as C square T T dash is equal to K into K square. Okay. And C minus V into C plus V. A plus V into A minus V. C square minus V square T T dashed. Isn't it? I am just multiplying 5 and 6. Now, can you cancel some of the terms? T dashed, T dashed can be cancelled. Now, what are we getting? Therefore, what you are getting is C square is equal to K square C square minus V square, which can also be written as, if you take C square common, it is 1 minus V square by C square. So once again, by what is the purpose in writing like this? The C square terms get cancelled, and what we get is, from this, what we get is K square is equal to 1 by 1 minus V square by C square, or K is equal to 1 by 1 minus V square by C square under root. So this is the constant of proportionality with which your frames of reference S and S prime, the distances are compared and are measured in relative motion. So I don't remember the equation number. I think it is 7. Just tell me whether I am following the sequence. This is your equation 7. This is a very important relation it's giving between these two. So substituting back into which relation? X dash. What is X dash relation? X dash is equal to, this is the relation, X dash is equal to K into X minus Vt, and X is equal to this. So substituting this value of K into those equations, what is it that you are getting? What you get is X dash is equal to X minus Vt by 1 minus V square by C square under root. And as before, we are assuming that the frame is moving along X direction only. When it is moving only along the X direction, there is no change along the Y. So they remain same, and hence we write it like this. So these are your equations. Maybe you can write them all together as 8. Let us now find some more simplification of these terms. Let us see what these terms are. So dividing this equation throughout, let us say by C. Divide equation 8 by C. There is, see, I told you there is an answer for how. Y is only for simplification, because by doing this we get another expression and we attach physical significance to those terms. That is why we are doing this. So by doing this, what do we get? We get dash by c is equal to x minus vt by c into, I am dividing this by c, so by c into 1 minus v square by c square. V square by c square. I'm sorry. X dash by c is equal to, what's happening? X dash by c is equal to x minus vt by c into 1 minus v square by c square. Why am I writing this? Because once again use the previous relations. I can write what is x dash by c, that was nothing but t dash, because you have x dash was equal to ct dash, excuse me, and x was equal to ct. So because of this relation, you can write this as t dash is equal to t dash x dash by c. From here x dash by c is t dash, and from here x by c is t. So t dash is equal to, what can I write? This is x. 1 second, guys, got disturbed. Let me write. I think we've already taken down. X dash by c was equal to x minus vt by c into 1 minus v square by c square. So because of these relations, x dash by c is t dashed and x by c is t. I can write this as t dashed is equal to, what am I writing? One more thing. So on to the right hand side here, let me write it as c is common, isn't it? So c, when it is common, I am dividing this by x by c minus vt by c under root 1 minus v square by c square. So what is it that we are getting from here? X by c is nothing but t minus minus v t by c. Okay, so can I write it as v x by c square under root 1 minus v square by c square. This entire thing is in a bracket and its square. How am I getting? Is this x by c is nothing but t. Now how am I getting vt by c? Let us see what you are getting. Vt by c, how do you get? Okay. V is as it is. What is t? X by c. Isn't it? So what am I getting? This v by c is as it is into, in place of t I will write it as x by c. So it becomes, what does it become? It becomes v x by c square. And that is what we are writing here. So finally, what is it that we are getting is that t dash is equal to t minus vx by c square divided by 1 minus v square by c square under root. very important relation is what we are getting. So that relation what we are getting is t dash is equal to t minus vx by c square, or 1 minus v square by c square. This is an important relation, and we call this as, I think, equation 9. This is your equation 9. So, this is how the time of measurement is related in the two frames of reference. So, these equations, what are the equations? Equations starting from, let us say, x dash, y dash, z dash, t dash are referred to as Lorentz transformation equations. So let us write them all together. First equation is, what is the first equation? X dash is equal to x minus vt by root 1 minus v square by c square. Number 1. Then y dash is equal to y. Number 2. Z dash is equal to z. Number 3. Number 4. T dash is equal to t minus vx by c square under root 1 minus v square by c square. These 4 equations are termed as Lorentz transformation equations. Lorentz transformation equations. They are referred to as this. So when these are Lorentz transformation equations, we also have what is known as Lorentz inverse transformations. They are, so what should that be? You wrote x in terms of x prime. If you write x prime in terms of x, it is inverse. This is again relative. Which is inverse of what? A and A inverse, something like that. So now we will write x in terms of x prime. So x will therefore be x prime plus vt, isn't it? Divided by one minus v square by c square under root y prime is equal to y, z prime is equal to z, and very importantly, t is equal to, what is t is equal to? T prime plus vx by c square under root 1 minus v square by c square. So these are your inverse transformation equations. So today we discussed, as a summary, what all we discussed today. Let us see. that we discussed about the null result of Michelson Morley experiment, and because it is null, what is the significance of null? What is the significance of this effect? What is the significance? That there is no either result. This was proved to be wrong. Because it is proved to be wrong, there was a need for us to, next what did we do? We discussed about the postulates of special theory of relativity. We discussed about the velocity, the principle of relativity and principle of constancy of speed of light, which are nothing but the postulates of special theory of relativity. Then we talked about Lorentz transformations. And once you define Lorentz transformations, we also discussed about inverse Lorentz transformations. So this is what we have discussed so far. In my next class, we will be discussing about the consequences of Lorentz transformations. There are two important consequences, namely length contraction and time dilation. Many examples I have given you in your previous videos and previous examples. Okay, so we will do the mathematical aspect now, and we will be discussing about these consequences in the due course of time. So in the meantime, I will try to share what all videos I have, and this also I will be sharing. Please watch them. If I can show them in the class, I will show. Otherwise, please see at home and come prepared for my next class.